Good morning, ladies and gentlemen. My name is Feng Shen from Huazhong University of Science and Technology. It's my great honor to be here to present our research paper, which is titled GraBi, Communication Efficient and Workload-Balanced Partitioning for Bipartite Graphs. First, I would like to introduce some background knowledge. Distributed graph processing systems heavily rely on graph partitioning to evenly distribute the vertices and edges over computing nodes. Furthermore, graph partitioning determines the computation cost and the workload distribution during subsequent graph computation phase. Existing graph partitioning strategies can be roughly classified into two categories, edge cut and vertex cut. As shown in the above figure, edge cut equally distributed the vertices among computing nodes. It generates some vertex replicates and edge replicates to create a local consistent subgraph on each node. To be different, vertex cut equally distributed the edges among nodes. However, vertex cut only generates vertex replicates. In our work, we adopt the widely used vertex cut strategy. Besides, the replication factor, which is the average number of replicates per vertex, is also an important metric for graph partitioning. Next, we will introduce the bipartite graphs and the machine learning and data mining algorithms. In the bipartite graph, the vertices are separated into two disjoint subsets, and every edge connects one vertex each from the two subsets. Bipartite graphs have been widely used in machine learning and data mining applications. For example, the collaborative filtering problem predicts the missing ratings from users to items based on existing ratings. When this problem is abstracted as bipartite graph, users and items are constituted the two vertex subsets separately, and existing ratings are represented as the edges between these two subsets. To generate high-quality partitioning for bipartite graphs, we first investigate many bipartite graphs and machine learning and data mining algorithms, and obtain the following three observations. The first observation is that the vertex value in many machine learning and data mining algorithms is a vector of multiple elements. For example, the authors of cubes associate each vertex with a vector of up to 128 elements, and the users of Power Graph can configure each vertex value as a vector of thousands of elements. The second observation is that the sizes of two vertex subsets in a bipartite graph can be highly lopsided. For example, in the Netflix, the number of users is about 27 times that of movies. In English Wikipedia, the number of articles is about 98 times that of words. The third observation is that within a vertex subset, the vertices usually exhibit polar degree distribution. In other words, within a vertex subset, a few high-degree vertices connect much more edges than most other vertices. For example, both the vertex subsets in DBLP exhibit polar degree distribution. The above three observations motivate the partitioning framework that is specially designed for bipartite graphs. According to the first observation, each vertex value in machine learning and data mining algorithms is a vector, which introduces a new partition dimension. In this partitioning dimension, each vertex vector can be divided into multiple subvectors, and then these subvectors, rather than an entire vector, are distributed over multiple nodes. According to the second observation, the number of vertices in these two vertex subsets are imbalanced, which heighten the necessity of processing these two vertex subsets with different priorities. According to the third observation, the vertices within a vertex subset usually exhibit polar degree distribution. As a result, the computation time of a few high-degree vertices is much longer than that of other vertices, incurring imbalanced computation time among vertices. Therefore, it is necessary to distinguish the vertices of different degrees. Based on above three observations, we designed GraBi, a communication-efficient and workload-balanced partitioning for bipartite graphs. GraBi comprehensively exploited the above three observations of bipartite graphs and machine learning and data mining algorithms. Overall speaking, GraBi partitioned the bipartite graph first vertically and then horizontally to realize high-quality partitioning. First, we will introduce the vertical partitioning stage of GraBi. Traditional horizontal partitioning evenly distributed vertices or edges over computing nodes. As an example shown in the above figure, the edges in the sample graph are evenly assigned to 3 nodes, where a cylinder represents a vertex-vector. Therefore, in the horizontal partitioning, the whole vector of a vertex is assigned to a computing node. As a result, the inter-vertex communication happens between computing nodes, as shown by the red solid lines. The intra-vertex communication, that is a communication between the elements within the vector, happens within the computing node, as shown by the red dotted lines. According to the first observation, the vertex value in many machine learning and data mining algorithms is a vector of multiple elements. The vertical partitioning divides each vertex vector into several subvectors, which is also called vertex chunks. And then these vertex chunks are assigned to different nodes. For example, in the above figure, each vertex vector is divided into 3 vertex chunks, and the 3 vertex chunks are assigned to different nodes. Therefore, in the vertical partitioning, the whole vector of a vertex is divided into vertex chunks. As a result, the inter-vertex communication happens within the computing node, where the intra-vertex communication happens between computing nodes. According to the above analysis, when the number of layers L equals to 1, the partitioning strategy is totally horizontal partitioning, and the communication cost is dominated by the inter-vertex communication. However, when L equals to the number of computing nodes n, the partitioning strategy is totally vertical partitioning, and the communication cost is dominated by the intra-vertex communication. Thus, L should be chosen between 1 and n. GraBi cites L as the greatest common divisor of D and n, where D is the number of elements in each vector, and n is the number of computing nodes in the cluster. In this way, vertex chunk consists of D out of L elements, and each layer is assigned to n out of L nodes. To summarize, the vertical partitioning stage, vertex vector chunking, is simple element grouping for every vectored vertex. Next, we'll introduce the horizontal partitioning stage. In this stage, GraBi should assign the vertex chunks within a layer over n out of L nodes. Traditional partition stages don't distinguish the 2 vertex subsets in a bipartite graph and assign the vertices from different subsets uniformly. As a result, in the above example, the traditional partition stages generate 15 vertex replicates. According to the second observation, the sizes of 2 vertex subsets in a bipartite graph can be highly lopsided. GraBi gives the bigger vertex subset a higher priority and assigns its vertex chunks first within each layer. As a result, the generated vertex replicates only come from the smaller subsets, thus setting a lower upper bound to the number of replicates. For example, in the above figure, by assigning the bigger vertex subset first, the number of replicates is reduced from 15 to only 8. Furthermore, according to the third observation, the vertices within the vertex subset often exhibit power law degree distribution. As an example, shown in the above figure, since the vertex chunk 5 connects more edges than the vertex chunk 6, the vertex 5 will consume more computation time in each iteration of graph algorithms. To identify the high-degree vertex chunk, we define a parameter R per vertex, as shown in the above figure. If the degree of a vertex is higher than this parameter, then the vertex chunk is identified as high-degree vertex chunk. Besides, GraBi uses a set of hash functions to assign the vertex chunks over nodes. For example, since the parameter R per vertex is 2, and the vertex chunk 6 connects 2 edges, GraBi uses the first hash functions to assign the vertex chunk 6 to one computing node. To be different, since the vertex chunk 5 connects 4 edges, It is identified as a high-degree vertex-chunk and is finally decomposed into two subchunks. As a result, GraBi used two hash functions to assign the generated subchunks over two different loads. By distributing the subchunk of every high-degree vertex chunk, GraBi achieves balanced computation time for all vertex chunks. Besides, to locate all subchunks of a given vertex chunk, the hash functions adopted by the vertex chunk should be recorded. To this end, GraBi maintains a table to store the hash functions adopted by every vertex chunk. Let's give a summary about GraBi. GraBi partitioned the bipartite graph first vertically and then horizontally. To improve partitioning quality, in the vertical partitioning, GraBi divides each vector of text into several subchunks. As a result, the bipartite graph is divided into several layers to strike an appropriate trade-off between inter-vertex and intra-vertex communication. In the horizontal partitioning, GraBi gave the bigger vertex subset a higher priority and assigned its vertices first within each layer to reduce the number of replicates. And then GraBi decomposed each high-degree vertex chunk into multiple subchunks and used a set hash function to evenly distribute the generated subchunks over computing nodes to balance the computation time among vertices. It can be seen from the above summary that GraBi is a fine-grained and high-quality partitioning framework. Besides, GraBi requires no prior knowledge or repartitioning stage. Therefore, it is lightweight. Finally, GraBi is not defined to a specific algorithm, and thus is generatable to most machine learning and data mining algorithms. Next, we will evaluate the performance of GraBi. GraBi is implemented on an open-source distributed graph processing system powered narrow, and the two important parameters in GraBi, the number of layers and the amplification factor alpha, are set as 4 and 2 respectively. We compare GraBi against the three existing partitioning frameworks. To be concrete, Bipartite considers the third observation, Bipartite considers the second observation, and the 3D partitioner considers the first and second observations. However, our GraBi considers all of the three observations. The experiments are conducted on an 8-node cluster. Each node has 8 physical cores and 16 GB memory. We use 5 real-world bipartite graphs and 3 popular machine learning and data mining algorithms to evaluate the performance of GraBi. First, let's evaluate the overall performance. This figure presents the total execution time of the 4 partitioning frameworks, where the total execution time includes the graph partition time and the graph computation time. Overall speaking, GraBi improves the execution time by an average of 1.65 times over HybridCat, 1.7 times over BCat, and 1.09 times over 3D partitioner respectively. To be specific, GraBi surpasses HybridCat and BCat in both the partitioning and the computation phases. Besides, GraBi outperforms 3D partitioner in the computation phase, but slightly underperforms in the partitioning phase. Next, we'll break down the performance into the graph partitioning phase and the graph computing phase respectively. Let's see the performance in the graph partitioner phase first. This table shows the replication factors achieved by the 4 partitioning frameworks. Overall speaking, the average replication factors achieved by HybridCat, BCat, 3D partitioner, and GraBi are 3.06, 3.28, 1.36, and 1.45 respectively. As we can see, due to the vertical partitioning stage, the replication factors of GraBi and 3D partitioner are much lower than that of HybridCat and BCat. The graph partition time includes graph loading and distributing time, as well as the finalizing time. The left figure compares the graph loading and distributing time of the 4 partitioning frameworks. As it shows, BCat has the shortest loading and distributing time, and HybridCat has the longest. The right figure compares the finalizing time of the 4 partitioning framework. The finalizing time is almost proportional to the corresponding replication factor. Therefore, The fertilizing time of GraBi and the 3D partitioner is much shorter than that of hybrid cat and bcat. Then, let's see the performance in the graph computation phase. The above three figures compare the lateral traffic of the four partitioner framework when executing different algorithms. Overall speaking, graph reduced the lateral traffic in hybrid cat and bcat by an average of 14.5% and 49% respectively. However, GraBi incurs more lateral traffic than 3D partitioner by an average of 11%, because the verification factor of GraBi is slightly higher than that of 3D partitioner. The above three figures compare the computation time of the four partitioner frameworks when executing different algorithms. Overall speaking, GraBi outstrips hybrid cat, bcat, and 3D partitioner by an average of 3.2 times, 3.41 times, and 1.3 times respectively. GraBi outperforms 3D partitioner because GraBi considers the power law degree distribution inherent in bipartite graphs and balance the computation time for all the vertices. We next compare the scalability of the four partitioner frameworks. The left figure shows the scalability in the graph partitioner phase. As we can see, the scalability of 3D partitioner and GraBi is better than that of hybrid cat and bcat. The right figure shows the scalability in the graph computation phase. As it shows, the scalability of hybrid cat and GraBi is better than that of bcat and 3D partitioner. At last, we'll explore the impact of two important parameters on the performance of GraBi. They are the number of layers L and the amplification factor alpha. As the left figure shows, the ALS and SD algorithms behave best at different L values. However, citing L as the great common divisor of N and D delivers adequate performance for both of the two algorithms. The right figure shows the impact of alpha on the computation time of ALS algorithm. As it shows, the impact of alpha is moderate and stable within a wide range. Finally, let's conclude this paper. This paper proposes GraBi, a communication-efficient and workload-balanced partitioning framework for bipartite graphs. GraBi partitions a bipartite graph first vertically and then horizontally to achieve high-quality partitioning. First, in the vertical partitioning, GraBi vertically divides each vector vertex into several vertex chunks, such that the bipartite graph is divided into layers to trade off between inter-vertex and intra-vertex communication. And then, in the horizontal partitioning, GraBi assigns the vertex chunk in the larger subset first within each layer to decrease the number of replicates. Finally, GraBi decomposes each high-degree vertex chunks into several subchunks to balance the computation time for all vertices. That's all. Thank you for your listening.